Hello, everybody. Good morning, good afternoon, good evening for everybody. I would like to welcome our guest today. We are from the IEEE 5 big chapter, joint chapter, San Diego chapter, SSCS, AP, CAS, ED, and MTT. And we'd like to welcome our guest, Venu Bhagavatula. He will be giving a talk today about insights into transceiver design for 5G millimeter wave UE cells. And Mr. Venu is working in advanced circuit design group at Samsung since 2014 in San Jose, USA. And he is a technical program member for ISSCC and DL for IEEE Solid-State Circuits Society. With that, we'd like to welcome Venu, and we are eager to hear your talk. Thank you very much.
Thanks, Mohammed, for the kind introduction, and thank you for inviting me for this lecture. Today, I'd like to share some insights into what have been the recent developments in the field of transceiver design for 5G millimeter wave equipment. So, as all of you know, there have been some mobile phones equipped with 5G millimeter wave transceivers are rolling out into the market right now. I think since last year. It's still early days, but there has been a lot of interesting work that has gone into these transceiver designs over the past 5 to 6 years. A lot of that is already in publication. There have been contributions from the academia, from industry. So there are a lot of interesting aspects of transceiver design already out there. In the course of today's lecture, I'd like to tie in some of these innovations to see how the application is driven by the requirements from the mobile phone. So this is a brief outline of how I've organized the talk today. I'd like to give an introduction of where 5G, why 5G millimeter wave is actually being talked about. And to put it in context, I'm going to try and contrast the requirements of 5G FR2. FR2 stands for the frequency range 2, which is another terminology used for the millimeter wave band. So to put these innovations in context, I'd like to talk about why 5G FR2 is different from cellular communication. I'll start with talking about architectural level options. What are the trade-offs that we can envision, especially when you try to put this transceiver on a mobile phone? And I'll take one step, I'll go one step down to say, based on these architecture level options, what are the challenges that are faced on both the transmitter on the receiver side? And finally, my main area of work is in the field of RF and analog IC design, but there are obviously many new areas where there are interesting problems to solve within the field of circuits. So I'll just give one example of another domain where 5G FR2 is opening new opportunities for innovation. I also planned for like a 5-minute break in the middle of the talk after I go through half the presentation. So if there are any questions, we can split it up there. If you'd like me to answer some questions to help you understand the talk better, then we can tackle that. We can handle that in the intermediate 5-minute break. So starting from a basic block diagram for a transceiver, any digital transceiver can broadly be classified into 3 major subsystems. You have the heart, or the main workhorse of these transceivers, the DSP, which would be the modulator or the demodulator on one side. And on the other end, you have the core analog circuits that actually interface with the physical medium. You have power amplifiers and LNAs, which drive the antennas, and up converters and down converters to modulate the signal to the carrier frequency. And at the interface between the two blocks, you have the mixed signal circuits, which take the digital input and give an analog output. in the context of cellular transceivers, especially cellular transceivers going into mobile phones, the partition has been over a period of time. So cellular transceivers might be under development for like close to 25 years now. Let's say from 1995 to 21, 26 years. So we've had multiple generations of cellular transceivers, and the classification of, if you take this initial transceiver block diagram, the partition of the system into different chips has been fairly standardized now. So if you take your communication processor or the modem, this generally is implemented in the most advanced technology node. So this is a digital processor. It's the workhorse which is doing all the number crunching, and it benefits from having faster switching transistors. So as you go into more advanced CMOS technology nodes, the processor generally follows the trend. On the other side, you have the front-end module, which are core analog circuits where switching speed is not as significant. These, say the power amplifier where RF performance is the key. These circuits tend to get integrated onto a RF-friendly process, which could be any sort of 3-5 process, which is efficient for power delivery and low-loss switches. So these two are in different technology nodes. And in the middle of these two, you have these multi-mode RFICs. Now, this RFIC is generally implemented in CMOS, but it's not in the most advanced technology node. So here, we'd like to take the advantage of CMOS being a digital-friendly process to do more digital calibration, integrate the PLL, have more digital components in the chip to allow for configurability. So this is a single chip that has to support, say, 2G, 3G, 4G. So it has to be able to reconfigure between many different modes, which is enabled by implementing it in CMOS. But it does not have to be in the most advanced process. So this is the system partition that was fairly standard in low frequency cellular, or say up to 4G. But then now that 5G has come in, it's been a big game changer. So that entire partition which people accepted as the standard transceiver chain, that is being revisited now, because 5G, especially the millimeter wave band, has gone onto a completely different frequency range. Previously, we were operating in the frequency range of less than 6 gigahertz, but now the new frequency bands that are coming up, which need to be supported, are in the range extending from 24.25 all the way to 43.5. So they're much higher frequency, and the loss that the atmospheric loss at these frequencies forces our hand to go into newer architectures. Okay, so broadly, there are 3 bullet points that we need to consider. The reason why people are even considering 5G NR at this stage is, you can do much higher download speeds. The download speeds are enabled by the fact that we're going to millimeter wave frequency, where the spectrum is, there's more spectrum available. You aren't in the low frequency band, we were sharing spectrum with Wi-Fi, Bluetooth, ISM band. So there are many different competitors to the same frequency band. And also over time, the frequency spectrum has got fragmented between many different carriers. So moving to millimeter wave band allowed for effective reset, that now again, you have a very fresh frequency band which has not been fragmented yet. And then you can design your communication system so that more bandwidth can be allocated per user. More bandwidth allows us to do faster communication, higher data rate, which then enables many sorts of new services. So that's the thought process by which people have said that from an overall user perspective, there's a benefit of going to millimeter wave. The other key innovation that has come about is the standard is designed such that it supports low latency, reliable transmission. Low latency is important when you're trying to get more real-time feedback. So if you're trying to go into an application where, say like a car radar application, where whatever communication has to happen, it has to happen with a very low round trip time. the 5G standard has evolved to support that. Now, this particular requirement did not have a major impact on the RFIC design, but I include that here just to say that that is also one of the big selling points that people claim for the 5G and our communication system. But because of the large path loss at millimeter wave frequencies, definitely some new architecture techniques are required. In the context of this talk, I'm just going to give a very quick primer on phased arrays. The idea is presented using these three cases. So consider case one, you have a transmitter delivering a power P, and you're trying to communicate with the receiver at a certain distance. Assuming that your transmitter is associated with an antenna that has an isotropic radiation pattern, it distributes the energy equally everywhere on the sphere. So your receiver only receives a fraction alpha p, where alpha is less than 1. The reason being that all the energy that is radiated in directions other than where the receiver is placed is eventually lost. So because of your link budget requirement, if you need to boost up the power received by the power received, then by a factor of 2, then your transmitter has to boost up his power by a factor of 2 as well. The concept of phased arrays is to use the spacing, to space your antenna, to use 2 transmitters, associate them with 2 different antennas, and ensure that, and then the distance between the antennas is such that you get a coherent addition in the direction where your receiver is placed. So here, if you have n elements, you get an n square boost in the effective isotropic radiated power in the direction where the receiver is placed. And as your receiver moves to different points along this sphere, you can direct the beam in that direction by introducing a phase offset between the 2 transmitters. So to take the point to compare here is case 2 and case 3. In case 2, you have a transmitter delivering a power 2p. And in case 3, we have 2 transmitters delivering a power P each. But the receiver in this case 3 is getting two times higher power in his at the point where he is placed. There are other points along the sphere where the received power is obviously lower in case 3, but that doesn't matter because the receiver is not located at that point. So the idea of directing the beam where the final recipient is the key concept behind phased arrays. And that allows us to reduce the complexity on the transmit side in the link budget. And you can see that if you compare this with our conventional cellular transceivers, the challenge is very clear that now you're increasing the number of elements, so your silicon area increases. Moreover, you're increasing the number of antennas. So in a device like a mobile phone where space is constrained, you have to come up with some ways of actually embedding these antennas onto the phone without blowing up the size of the phone. So there are limitations on how far you can scale this idea in a mobile phone compared to a base station. A lot of base station publications you'll see have a 256 antenna elements because they can afford to do so. On a mobile phone, you're more tightly constrained because the size of the mobile phone cannot increase to the same degree. Okay. To put down some numbers on where the differences are, you can think about it first in terms of frequency of operation. LTE or even the sub-6, 5G has 2 bands. There's FR1, which still comprises the frequencies less than 6 gigahertz, and there's FR2, which is a millimeter wave band. So LTE and sub-6 5G are more below 6 gigahertz, and they follow the more, so that's the frequency range that we were more familiar with in the past 2 decades. So the architectures are of a similar nature. Whereas FR2 which is moving up to 43 gigahertz, is using phased array technologies. And if you follow the trends, then it seems that 5G FR2 might actually go to higher frequency bands as well as the standard develops. The function of the CMOS RFIC is really interesting because in the initial block diagram that I showed, I said that the multi-mode transceiver was in CMOS, but the PA and the front-end switches had moved into were in a FEM. So there were two chips effectively. But if you think of 5G, because you have all these different antenna elements, if you have to have multiple PAs, what is the more efficient solution? Should we still go with this two-chip architecture where you have a PA at one place and a multi-mode function in CMOS, or can the whole system be embedded into CMOS? So that's a new question. The answer is not clear yet. So different people, there are many every company is trying to play to their strengths to try to understand how they can contribute in this evolution. In terms of the power levels, if you so here I'm talking about power levels from the perspective of the CMOS IC. In LTE, because the CMOS IC was driving a FEM, the power levels within the CMOS IC would be on the order of maybe 8 dBm, 6 to 8 dBm, depending on what the gain of the power amplifier was. But for 5G, if you want to do everything in CMOS, then the output power needs to be much higher to support the link budget. In terms of architecture, most transceivers, again, it's difficult to make sweeping statements, but most published transceivers, if you go to IEEE for the past, like maybe if you go to any of these IEEE publications for the past 10 years, you'll see that most LTE transceivers, both transmit and receive side, were a single step up conversion. So you have your baseband IQ going up to the carrier frequency in one step. For 5G, again, that I'm going to go over some architecture options in the next few slides. But for 5G, that whole question has been revisited. Is it more efficient to, when your carrier frequency is as high as 43 gigahertz, is it more efficient to generate your quadrature LO, quadrature clock signals at 43 gigahertz, or is there a more efficient way to do it? So that question in terms of LTE was closed. In my experience, I didn't see people debating whether to do super heterodyne, at least in the last 10 years. But for 5G, that's again been an open question, which is interesting. And finally, the chip definition should be a single chip. Even the transceiver part, should it be two chips? These are interesting questions that have been revisited in the context of 5G millimeter wave. So I'll move to the next slide quickly. Here, I just want to highlight that now the UE transceiver architecture, the blocks that we need to consider are, you have the modem, you obviously have you still have the mixed signal blocks, the A to D and D to A converters. Here I give an example of something where you have one mixer. So you have one mixer to convert the low pass filter up to the carrier frequency. You will still need a phase shifter to support these multiple elements. So here I take the example of two data streams. You have one data stream going on the H polarization, the second data stream going on the V polarization. The example here shows 4 elements on the H path, 4 elements on the V path. In order to steer the beam, as I showed in a preceding slide, we need to introduce a phase shift between the different elements on the H polarization, so we have individual phase shifters. So this is one of the multiple architectures, but I just wanted to show one block diagram to describe the multiple blocks, and next we'll try to motivate what are the different architecture options we have. In the context of when we evaluate these different options, it's important to think of it in the context of the mobile phone for this specific talk, because we'd like to gain some insights on how 5G is getting embedded into mobile phones. Now, so we said, so what are the constraints for a mobile phone? First, area is limited. So you can't really have very big chips. You can't have very big arrays. Second, if you're a mobile device, your relative location between you and your base station is constantly changing. If depending on how you hold the phone, if you hold the phone along the sides, if you hold the phone like this versus if you hold the phone like maybe this, you might have different different transmission characteristics. So you need to have multiple antennas to account for different ways in which the users might hold the device. So the key take home is that you're going to have multiple antenna modules on your phone. Now, if you try to embed too much into the antenna module, then if you can say, as you introduce more functionality into the chip becomes bigger, it becomes more expensive. Once you have established that we need multiple antenna modules on the phone, having one all-powerful chip means that you need to have multiple of these all-powerful chips distributed across the phone, which takes area, takes power, takes real estate. So from that context, it makes sense to have the core functionality sitting at a central location and then distributing the antenna modules along the different peripherals of the chip, different periphery of the chip. So that makes it a multi-chip solution, which then comes with its own set of challenges. So let's talk about the architecture options at this point. So the first architecture option is what we'll call the RF interface. Here you have a I'd say this is the easier one to explain, that your modem communicates with an RFIC. So it has baseband signals going back and forth. The modem can be implemented in the most advanced CMOS process. You put your CMOS RFIC as a single shot up converter. So it takes your baseband IQ signal, up converts it into the carrier frequency. And then you have antenna modules placed at closer to the periphery of the phone. So the RFIC and the modem can be at a central location. And connecting these two, you have a cable which is operating between 24 to 40 gigahertz or whatever your carrier frequency is. So there are a few advantages and a few disadvantages. The advantage is that the phased array chip is relatively simple. It's purely a beamformer. It has a PA, LNA, and a phase shifter. So there's no PLL. You don't need to synchronize the two chips. So most probably your this beamforming chip can be implemented in technology that is very amenable to just your RF performance. You don't need to most for your RF performance. But the challenge with this approach is obviously that you have this cable which is operating at a very high frequency across these two chips. So as the frequency of the cable increases, it will have more loss. If you want to have less loss, then you need to pay more for it. So there's a trade-off in terms of bill of materials and the analog complexity. But this architecture is quite suitable if you have a large array size, because then you just have one central block and then you can focus on your beamformer and distribute it across a large array. So this architecture is quite popular and you'll see a lot of publications which use this particular architecture. The second is IF interface. So here what we're saying is that we're going to do the up conversion in two steps. The first step, the baseband signal is only up converted to an intermediate frequency to reduce the cost of the cabling between the RFIC and the beamforming IC. But now you need to have a second up conversion in the phased array IC, which requires you to synchronize the clocks of the two signals. So you need to send a reference clock along with your IF signal between these two chips. The IF signal has so the IF cable has a smaller loss, but you add this complexity in terms of implementation because now your beamforming IC is a bit more heavy. The third is a brute force option. This is where I would say that the chip that sits on the antenna module is all powerful. It just takes a baseband input and sends it to all the chips across the chain. And there you have a single step up conversion going to the phased array section. Here the phased array cost would be more because obviously it will be a bigger chip, but and also you have multiple baseband IQ lines running across the chip. But here you eliminate the need of any RF cable connecting RF cable on the phone. Architecture 4 is just an amalgamation of maybe architecture 1, where I say that if you don't want to have two different chips in the front, so if you look at architecture 1, the RFIC and modem are included in different chips. Maybe the RFIC can be a couple of generations behind the modem in terms of the CMOS technology, but if for whatever reason, if there is a benefit to the bottom line, if you embed this into a single chip solution, then this is also viable. Obviously, moving analog circuits to advanced technology nodes is generally challenging, but sometimes reducing the number of interface lines between the modem and the RFIC also has benefits. So this is another valid architecture choice. So in this talk, I'm speaking not as someone who works at Samsung, but more as an SSCS member. And if I look at publications out there, I think the question is still open. What is the optimal interface is an unanswered question. People are still trying out these different options because there are trade-offs associated with all these different approaches. And eventually, what drives us towards one architecture option might not even be a circuit constraint, but it could be a cost constraint or how the other chips are being developed in parallel. So, but all four options are viable and result in interesting circuit design challenges. So I'd like to take if there are any questions at this point, we can discuss, or if there's anything that you think which I've spoken about, which needs to be explained in more detail before I proceed to the next part of the talk, then we can do that now.
Yeah. Thanks, Venu, very much for this detailed kind of introduction. It was like very good, starting from the basics and then showing the whole picture to the whole community. Yeah, so in terms of the architectures, you mentioned like there are like 4 options kind of we have. So in terms of like, you mentioned also that this will be maybe derived by other factors in terms of like, and not completely circuit design, but from circuit design point of view, for example, from power consumption, is there any of them that is like distinguished, or they can be still all very familiar, like very near to each other in terms of performance, power consumption? Because, for example, like traditionally, the military applications are using super heterodyne because of it's the best kind of performance in terms of intermodulation and these stuffs. So yeah, maybe if you just give us some like brief comparison in this regard, this will be good. Yeah.
Sure. So if you look at the overall power consumption, so like most transceivers, the power consumption is in the transmit mode is driven primarily by your power amplifier. The power amplifier is the biggest power hog in the system. So any architecture choice that allows for implementing the power amplifier in a more friendly process generally benefits in terms of overall power. So for 5G, it's a bit more tricky because 5G is a TDD system, and it's a TDD system with a high. The goal of 5G is to provide a larger bandwidth so that your downlink speeds could increase. So a large fraction of the time the receive is on. But if you think of a system with a 50% TX, 50% RX duty cycle, then most probably having say an architecture 1 where your PA is in a process that is most suitable for improving PA efficiency, you most probably would benefit from that. Having said that, the power is not the only challenge. So I wouldn't say that architecture 1 wins in every way, but to answer your question from a power consumption perspective, it's likely that architecture 1 would allow for a lower power PA.
Got it. Okay. Yeah. Thank you very much. And also for the new bands, you mentioned also in the very beginning about the bands. So and also there will be new bands. So what are the challenges with the new bands, especially when we are going higher and higher in frequency? From your experience and from your like both industrial and applications, like publications. Yeah.
So there are a few challenges with going to higher frequency band. First, I guess, is purely from a circuit designer perspective. Even if you're in the same technology node, you can think of it for the same Fmax going from 24 to say a 48. Let's assume 48 comes sometime in the future. It's still a 2x increase in your carrier frequency. So the maximum gain that you can achieve out of a single amplifier stage is reducing, and that has its set of problems because maximum gain you can get is reducing. So then you start adding more stages in your system, and when you add more stages in your system, then your gain variability increases. So transceiver design itself is becoming more difficult.
Challenge.
The other challenge that I see is the antennas, because you obviously don't want to make a solution which is very specific to one band. And if you look at, okay, I wouldn't speak too much about antennas, that's not my area of expertise, but I would say that trying to design a power amplifier that can provide an optimal impedance over a wide frequency band so that as your antenna impedance varies, say from up to, if you're using an antenna for say a high band from 37 to 48, then the antenna is not going to provide exactly 50 ohms over that wide frequency band. So trying to co-optimize that interface between the PA and antenna over such a wide frequency band also brings its share of challenges. So higher frequency and wider bandwidth both are important problems that we have to solve.
Yeah, and well, we also have like two questions related to the antennas, like what are practical array sizes being developed? This is kind of a question that we have, like in terms of array size. I think the module sizes, what are the practical ones? Yeah.
At least, so I won't go into specific details about what are being developed for I would say the ones that we have seen in the market where we have seen teardowns already being presented. I think there are antenna modules with 2 elements, antenna modules with 4 elements that I've seen being more popular. Other than that, I don't see very large number of elements coming out. So they could be smaller depending on application, but I would be surprised if I see very big module sizes compared to that.
Yeah, because we are like in UE and UE should be very light. This does make sense. Yeah. I think the last question that we have is about the RF loss associated with splitting signal among the different antenna elements. Like like is this a big issue in phased array systems, and what are approaches to minimize that?
Okay. So we're talking about splitting
Splitting,
the
yeah.
signal
Splitting.
between different antenna elements. So the splitting is happening. So in a few ways, it's good. We're not splitting the signal after the PA. We're splitting the signal at a low power interface because every antenna has a dedicated power amplifier. So in terms of signal splitting, it's always best to do it at a point where your power level is, if your noise budget allows for it, it is better to split the signal at a point where your power level is not high because uh, you don't lose efficiency. The way to mitigate it is the standard. You just have to put more gain stages. There's no way around it. Generally, it's, oh, let's see. Let me see what I can say on this. Um, Yeah, interface design is important. If you're trying to split a signal from say one stage to 4 different stages, then making sure your impedance match when you split across multiple stages is that all your interfaces are well matched, keeping your blocks close together so that you don't have additional distribution loss. So floor planning is important, but the final solution to all the problems is just to add more gain. Unfortunately, there's no way around that.
Yeah, yeah, and if you can do it in lower power, this will be not be hitting your kind of
Yeah.
frequency and power consumption. Yeah, I think this is good. I think we can continue. Can you make the presentation full screen if possible? The bottom, yeah.
With,
Uh, Yeah.
Is
Yes. Yeah. I can see it. Yeah. Thank you, Venu, very much.
full
We
screen
are going
right
to
now?
continue listening to your talk. Bye.
Okay. Okay. So moving forward, the architectures that I've presented, that they're already very highly cited papers that have discussed this. Here I'm giving reference to a paper from Broadcom, published both at the ISSCC and the JSSC. This was like this was one of the first, I'd say, big integration chips, which spoke about both the IF section and the RF section, and also the challenges associated with the interface between the module and the antenna. It was for a 60 gigahertz application where they had a IF interface and the cable, the single cable connecting your IF chip with the RF chip included both your reference clock, the control signals, the IF frequency. So it introduced the concept of embedding the reference clock and control signals within the IF line so that you can reduce the number of dedicated IF lines connecting the two chips. Now, we do talk a lot about phased arrays, but one interesting paper that got presented, which I feel didn't get a lot of attention yet, is there are interesting trade-offs associated with the number of array elements, which is also one of the questions we just addressed. So let's take this example. Uh, in this paper, they made a comparison between two different cases. One was a mobile phone with a phased array with 4 elements, and the second was a phased array with 2 elements. Now, the goal for going with 4 elements is obviously that you can push out your, compared to 2 elements, you get that n square benefit. So 4 elements, 4 square, 16, 2 square is 4, so you get 4x higher EIRP at a specific location, which simplifies your link budget. Now, what was presented in this paper was that if you go with 4 elements, because of the way the battery is placed in the phone, the thickness of this element forces a reduction in the size of the battery. Because now this is product design. Once it goes into product design, it really is not in the hands of the circuit designer. This is a higher level decision. So as a circuit designer or a wireless system designer, if you propose a 4-element phased array, what gets triggered is a battery size reduction, which then results in the total battery capacity, which they said was a 7.4% reduction in capacity and effectively talk time. You can think of this way. If you ever read these phone reviews, people are very particular about how long your battery lasts. So this is a design choice that can have a big implication. On the other hand, if you have 2 elements only, then your battery size can be recovered, and you can reduce the reduction in talk time to about 1.7%. So this is an interesting trade-off, because you can see that going with 2 elements, if you have to hit the same EIRP as 4 elements, you have to push out higher output power. If you push out higher output power with 2 elements, you most probably would need to go into a different technology, maybe not CMOS, you might have to go into a different technology. Because to push out higher output power, you might need to have a larger supply voltage. So that changes the design of your PMIC, that changes the technology of choice of the power amplifier. In contrast, if you go for 4 elements, maybe the per PA power requirement could reduce. Your PMIC design could go for a lower supply voltage, and you can implement your PA in CMOS. So both these design choices seem to be valid design choices, but eventually the decision might lie on what's your battery lifetime. So it is a multi-dimensional problem. As circuit designers, we bring our ideas to the table, but once you start integrating it onto the phone, how topic A couples to topic B, and how that ties into the final form factor, these are very interesting trade-offs for which there is no linear path for the correct solution. These are different optimizations that we can just present. Now, focusing on the phased array work. So the phased array, there has been a lot of a lot of good work that has already been done in this area. I'm picking just some industry papers at this point, but obviously even academia has led the way in starting from, say, Berkeley, San Diego. A lot of schools have done phenomenal work in this area, but I'm just picking up two papers from the industry which were a multi-element phased arrays. So IBM in 2017 presented their 28 gig 32 element phased array in SIGI. Broadcom, one I referred to previously, had a 16TX, 16RX in a 40 nanometer low power CMOS process for a 60 gig application. So these papers were significant in my mind because they transitioned, say, millimeter wave communications from research efforts to final products. And Broadcom's paper also was a good example of the scale at which this whole system could be viable in CMOS. So these are interesting, works that came out. But just to summarize this part of my talk, there are several factors that need to be taken into account when you decide this. When you decide the wireless system, you have your TXRX link budget, how many elements, what is the EIRP you want to target, what is your reference sensitivity requirement from a receive perspective. What's the order of modulation that you're trying to go for? The end user doesn't care about modulation. All he cares about is data rate. Data rate can come from two factors, bandwidth or higher order modulation. In sub 6, your bandwidth is limited, so you have to use higher order modulation, maybe a 256 POM, go to higher 512,024. At the promise of millimeter wave was that we're going to have a wider bandwidth. So then how high do we need to go in terms of modulation? So initial work was done with very basic modulation. You just had QPSK modulation, 16 QAM. But like everything else in life, we are also moving towards more complex systems in 5G. So now higher order modulations are also going to start coming into play. And because 5G is such a it closely ties between your the RFIC and the antenna. There are a lot of antenna choices that also get tied in. A lot of antenna implications or antenna co-optimization that gets tied in with the transceiver design. I'll skip this slide because I think I'm running behind on time. In terms of UE transmitter requirements, again, this is tied to the number of elements. You can see that depending on your application, your number of elements could range anywhere from 4 to 8 to maybe 16 to 64 or even larger if you're going for a base station application. For the UE, I think we're still going for a, I guess the term UE is slightly vague, that's user equipment. We're discussing this in the context of a cell phone, but if you have a user equipment, which could be a box which is sitting with the end user, then maybe the form factor is slightly larger and can hold a larger number of elements. Okay. Let me come to the So now for the remaining 15-20 minutes, I'd like to talk about some specifics in terms of the circuit related challenges. So the first one is the power amplifier. This has been like a hot topic of innovation, and every year you will see multiple publications trying to address this. If you want to do everything in CMOS for a phased array, you have to account for the fact that now you have multiple power amplifiers on the same chip. And all these power amplifiers are generating power on the order of, say, maybe 10 to 14 dBm, depending on what modulation you're referring to. So for sub 6, the distinction was clear. The PA was residing on a front-end module fabricating in a non-CMOS process. But if you have an antenna module, you don't want to have multiple chips on it. So if you can integrate everything within the PA, within the CMOS chip, there's a benefit of going there. Impact of technology scaling. You are still operating at millimeter wave frequencies, so we'd like to use the thin oxide devices, the low voltage devices, something that has a higher Fmax compared to the IO devices. However, this needs to be done while still generating higher output power. So if you want to generate a higher output power, you need a higher supply voltage so that your voltage swing could be higher. So there's a trade-off there. Higher voltage swing requires higher supply voltage would force us towards going with I/O devices which have better reliability, but large frequency, high frequency operation would take us in the direction of using low voltage devices. So this problem obviously was faced even in sub 6 gigahertz, but there the solution was to take the core, the GM device, the transconductance would be low voltage, and that would be protected with a I/O device as a cascode. But frequency prevents that solution from being efficient at millimeter wave. So I guess there has been work. I've referred to this paper from UCSD here where they introduced the stacked PA architecture. After this, there have been several more publications in this area where you say that if you you can stack multiple devices and use a higher supply voltage. And if these devices are designed such that you can couple the signal, you can couple the drain swing onto the gate of each cascode device, then you can effectively distribute the total voltage swing of the output across multiple devices. So even though you're using N times VDD as your supply voltage, where VDD is the nominal supply voltage for, say, one device in a given technology, if you can design the circuit or distribute the voltage across multiple devices, then you can still use low voltage devices and generate a high power at millimeter wave frequency. So this is an interesting architecture choice that I think has become more promising at these frequencies of operation. The second is challenge lies with purely efficiency reasons. As I said, that you have multiple PAs on the chip. If you're trying to do a 4-element phased array with both horizontal and vertical polarization, then you have 8 power amplifiers operating simultaneously. So again, I guess I missed a key point that 5G millimeter wave is still a TDD system. So you have transmit, receive, they're not operating simultaneously. And to couple both transmit and receive to the same antenna, you have a transmit receive switch. So how do you account for that? You're really trying to maximize your PA efficiency. So you want to eliminate all additional losses that come about after the PA. So if you take this example, I just say if you're delivering 15 dBm of output power and your PA is followed by a matching network and a TR switch, both which contribute 1 dB of loss, just to keep the numbers easy. Then at the PA drain, you're delivering about 17 dBm of power. So with 8 elements, it's about 1.6 watts. So there's a huge amount of power that you're generating on chip. There are obviously limits to which what you can achieve in terms of PA efficiency. So the main thought here is that we have to look at options which reduce the loss after the PA. So reducing the TR transmit receive switch loss is going to be a big win. And this problem has been addressed again in several papers where the trend that I see is that the system is biased in the direction of the PA. That's a common thing I'm seeing across all recent reports, that if you take this example, this is adapted from a paper presented in the ISSCC 2018, where you have so if you look at the PA signal path, you have the transistor. This was a common source final stage with a neutralization, followed by L1 and L2 with a transformer as a part of the matching network going directly to the antenna. So there is no switch added on the transmit path so that you can minimize any insertion loss on the transmit side. But you still need to reduce the receive path loading on the power amplifier. And this is done by adding a shunt switch on the receive path. And the way this operates is the inductor L3 can be designed as a lumped element equivalent of a lambda by 4 transmission line. So in the transmit mode, the transistor M1 is on. That pulls the one terminal of L3 to the ground. Since if this is a lambda by 4 transmission line, it transforms your short circuit at the drain of M1 into an open circuit at the antenna, and that allows you to deliver the PA power without loss on the receive side. So this is an example of how the receive side is taking the burden of reducing the loss on the transmit side, because on the transmit side, the goal is to improve the PA efficiency so that you can reduce the amount of temperature, reduce the amount of power consumed during transmit mode, which would help to keep the module temperature in control. So that's the key take home of the slide, that the direction people are going are the big challenge is PA efficiency, and the direction people are going in terms of optimizing TR switches to eliminate all additional switches within the TX signal path at the expense of potentially degrading RX performance. Now, taking an example of on the receive side. Now, so we spoke about one challenge on the transmit side. On the receive side, the challenge is really what can be done in terms of reducing the area. We said that for applications on the mobile phone, the size of the phased array RFIC is very critical. If you have dedicated paths to do transmit to do all the different bands. In this example that I show, I'm assuming a transceiver which has different front ends for 28 and 39. So the first example is you have 4 elements: TX28, RX28, TX39, RX39. So you have 4 elements, and so you have 4 different circuit blocks to cater to these different bands. We can potentially reduce the size if we come up with an architecture where 28 and 39 can be combined into a single chain. Now, there are complexities in the antenna which I'm not addressing, but purely from a circuit design perspective, then maybe if we can come up with architectures that can combine 28 and 39, then there is potential saving. For the TX side, as I said, efficiency is important. So if combining 28 and 39 results in efficiency degradation, that is most probably not a acceptable solution. For the receive, it's possible that maybe we can design a more wideband circuit to get better performance. So there's this interesting paper that came out last year where they demonstrated an LNA with a very flat LNA, VGA, and vector modulator all included with a very flat response from 20 to 50 gigahertz. So this is the direction I think we'll see more work in the near future, because die size is a big deal in terms for 5G applications, not merely for cost reasons, but also just because of the physical area available on the phone. And this sort of work opens the door for shrinking the chip size, because you're pushing in more functionality within a smaller silicon area. The next is carrier aggregation. So if some of you follow work in the field of cellular, you'll see that carrier aggregation has right now on the receive side for LTE applications. I think the recent publication from Samsung had like six-way carrier aggregation. So it can pick up 6 different chunks of bandwidth and combine it and provide it to one user. So this is an LTE. 5G has still not reached that stage. There is still only initial discussion going on for even at the standards level, what sort of carrier aggregation needs to be supported? Does it need to be interband or intraband? All those questions are still not finalized. But there was an early paper in 2019 where they discussed about how carrier aggregation could be implemented. So they have this approach where the signal is down converted using 2 different LOs. But in this case, the challenge is how would the frequency planning be done? How would you select what FLO1 and FLO2 would be? So these are open questions. This one is not completely solved yet. The block diagram I show on the right is, let's see, is just the common source amplifier with a TIA, which yeah, lost my track of thoughts. I'm not sure what this is doing here, but I think I'll skip this one. This might not have been in the context of carrier aggregation. Okay, moving on to phase noise. Now, as I said, there are two directions for going to wider bandwidth. You need to have, if you want to have a higher data rate, you either need to go for wider bandwidth or you need to go for higher order modulation. Higher bandwidth, that is supported by the standard itself. So like what I spoke about, having this wideband LNAs, wideband PAs could help in that. But the next step is going to be in terms of getting better phase noise. So better, higher order modulation. Now, higher order modulation depends on multiple factors. Circuit impairments that could limit it would be, say, AM, PM, a distortion that occurs in the power amplifier. But for this, there is a path. Maybe you can do digital pre-distortion to correct for it. So there is some innovation on the circuit side and there is some correction on the digital side. But there is a path which we can go. Higher order modulation is also limited by circuit impairments such as IQ mismatch, gain variation. Here also there is some digital calibration techniques that can be employed to mitigate it. I'm not saying these are easy problems, but I'm saying that there is a path to figure out like how should we handle these things. But LO phase noise is, you cannot debate about that. It has to be low in order to meet these higher order modulation schemes. And for the same dB value, suppose your IPN requirement in terms of dB still remains the same, whether you're doing it at 6 gigahertz, at 40 gigahertz, the effective RMS jitter scales down as your carrier frequency scales up. So the challenge becomes much more difficult as we go to higher and higher frequencies to achieve higher order modulation. Now, there are multiple factors that contribute in terms of phase noise. But one that I'd like to just highlight here is if you just take your reference clock frequency, if you use in a cellular application, what frequency you use for your reference clock is very tightly coupled to all the other wireless platforms that exist on the cell phone. So you have GNSS, you have cellular, all of them might be sharing the same crystal oscillator. So you don't have flexibility to choose whatever reference clock frequency you want. You're tied in with the demands of the other wireless chains as well. Keeping that in mind, you can see that if you use the same reference clock as a 6 gig transceiver for 40 gig, the amplification of the crystal oscillator phase noise is significantly higher. That being significantly higher means that now the whole LO generation architecture has to be designed keeping that in mind. So either you go with an architecture where you can minimize any additional in-band noise contribution from PLL circuitry, or you go with this architecture where you have a wider bandwidth, a smaller PLL bandwidth, so that you can low pass filter more of the crystal oscillator noise. The VCO noise gets high pass filtered. So now you have to look at architectures where your VCO itself, the inherent phase noise is low. So there are again trade-offs involved in the clock design, which are quite stringent. 9 o'clock. I'll talk about this slide. Now, power control in phased arrays is another very interesting problem. So if you think of what was done in cellular transmitters, there are two sorts of options that have developed. The first is to have a coupler off chip. Actually, the coupler is always off chip, and you can have a power detector either on chip or off chip. So if you're trying to make a high performance solution for a high-end mobile phone, then you could have an off-chip PA because you can afford to pay for it. The coupler would always be not on the CMOS die. And what the basic idea is, your power amplifier is delivering certain power to the antenna. A portion of that is coupled back to the power detector, which has a voltage equivalent of that coupled power. And then the modem can determine, can try to decode what is the power that is being delivered and take appropriate action. So you have one coupler, one PDET in a normal cellular transceiver. Now in a phased array, you don't have really one transmitter, but you have 4 different power amplifiers. So now the problem becomes a bit more difficult, because what you're trying to estimate is an EIRP, which is a function of 4 different power amplifiers. Each of these power amplifiers are driving different antennas, and these different antennas are working with different edge interface. So if you take a 4-element module, the antenna on the edge of the module will see a different environment compared to the antenna in the center. Therefore, the PAs which are driving the center antennas will see a different impedance compared to the edge antennas, and therefore they might deliver slightly different power. So depending on the EIRP accuracy, the accuracy with which you're trying to estimate the EIRP, you might need to estimate the power of each of these power amplifiers and then take a decision. Now, if you want to estimate the power of each of these power amplifiers, you need to have 4 different couplers and 4 different power detectors. Now, the module size is very small, so then having an off-chip coupler is extremely difficult, because that will just increase the size of your module. So trying to integrate all of this within a single die seems to make sense. So this is one recent publication that has come where what's demonstrated is a power amplifier with a short electrical length broadside directional coupler on chip. So this is not a lambda by 4 length coupler, but this is something much smaller. It's lambda by 30. And then this is followed by another circuit, a PDET circuit, or just a squarer circuit that takes the signal and converts it into a current and goes to the rest of the chip. So this is one idea for having these very small directional small power detection paths on chip, so that you can scale this across multi-elements of a phased array. But this is not the only idea. There are other ideas where people have spoken about more analog domain power sensing. So here the idea is power is a function of voltage into current, and the phase difference between the voltage and current. So if you can add a third winding into your PA bailend to sense the I load. So I sense is a function of I load. V sense is a function of V load, followed by a mixer. Then the output of this mixer and OTA, the VPDET function, is an indication of the true power delivered by the PA. So this is another technique which has been introduced, same in the context of doing good power detection while keeping everything on the die. The phase shifter is obviously one of the big circuits in your transceiver chain. You can there are different architectures for this. You can have an active phase shifter, you can have a passive phase shifter. This is fairly well referenced in journal publications. I don't have anything special to add on this, but I did include this in the slide deck just to highlight that compared to say cellular transceivers, phase shifters is definitely a new block that is have to be added in the phased array transceiver chain. So we're seeing it is challenging in itself, trying to get very fine resolution phase steps. But this is a block that is fairly well published and fairly well understood at this point. The last, I promised that I'm going to talk about one application that is a bit offset from my area of work, but I still think it's very interesting, so I like to bring it up. There's this the overriding goal that you can see is we need to improve the efficiency of the system. 5Gs can be power hungry because you're operating at higher power levels on the CMOS die with multiple elements. So any way in which you can improve efficiency, with either through pushing the TR switch onto the receive side or using stacked PAs and try to improve output power and efficiency, everything helps. On the PMIC side, one of the ideas that has been tried out is in uh, in 5G, they allow for symbol by symbol power control. So it's possible that you can have a waveform where, say, symbol 0, 1, 2, all the way up to 12 have low power, then suddenly 13 has high power, and then again goes down to the next a low power. So if you can modulate the supply voltage to the power amplifier with an accuracy of in each symbol, then you can reduce your overall power consumption, because every symbol you should be able to switch to a different power level. From a PMIC perspective, the challenge is that how can you switch between these supply voltages and settle fast enough during that transition time? So there is a paper about a fast transitioning buck converter that could switch between a high supply voltage or a low supply voltage to optimize power consumption significantly. So this is just an example of an innovation that is primarily driven by the fact that 5G is a power hungry system, and everyone has to chip in to figure out how to reduce the overall power. Again, just to summarize the top points I spoke about, UE still has significant challenges that need to be solved, especially if we want to go to 256 QAM downlink. Phase noise, I just briefly touched upon it, but wanted to say that's because of the fact that the reference clock is shared across multiple wireless standards. You don't have the flexibility of increasing it to what is most suited for 5G. So coming up with architectures, keeping that constraint in mind is important. The UE capability at this point is uplink limited. So a lot of the focus that we see is on the transmitter, how to improve PA, the P1dB efficiency, and how to keep the heat down by coming up with ways to reduce loss after the PA. Form factor is a big driving big factor which drives a lot of design decisions. We spoke about battery size, which is impacted by how many elements you select. We also said that pushing in the directional coupler on chip is pretty much driven by the fact that the module size cannot increase. Wideband signal paths are going to be more important moving forward. So ways in which we can design our circuits to be efficient and wideband will open the door for the next round of innovation. And finally, the whole UE architecture is really it's more of horses for the courses. So depending on what your application is, what you're trying to minimize in terms of your bill of materials, one architecture might be better than the other. So there's I guess the main take home from this whole talk is it's still an open area where there's a lot of chances to do interesting work. Yeah. I guess I covered these points in the preceding slide, that there are many challenges, and I think it's an interesting time to be involved in this field. Yeah, thank you. And I guess the final slide, I haven't, a lot of the work, I mean, some of the material here is from our group, but a lot of these slides and discussions to understand the different technologies has been through conversations and discussions with all my team members. So just like to acknowledge everyone in the Advanced Circuit Design group for contributing. Thank you.
Thanks, Venu, very much. Thanks, Venu, very much. This was very interesting talk, and this is like a very hot topic, and this is opening the door for more innovation and more understanding of the 5G kind of challenges and what are the directions for the future. And like this will be kind of a technology that is changing the whole world for better kind of connectivity. And yeah, thank you very much. I think we will host some of the questions now. Yeah, with that, after that, we should be concluding. So I think there is some of the questions related to the placement. So for the How can the aperture of the phone affect the antenna module placement on the UE? Maybe due to reflection or ground interactions. I think you touched base on that in terms of like the battery and how did you place the module. But I think the question was, in the placement of the antenna module and how can the aperture of the phone affect that specifically?
I'll have to admit, I don't have a lot of insight into that particular aspect. From a circuit design aspect, I can think of some directions, but yeah, antennas and aperture side, that's not an area I'm very well versed with. Sorry about that.
Yeah, okay. But I think it's like it was clear from your slides that the antenna module is just there are some decisions on that based on the battery, based on the phone. Yeah. And there is another question related to the process, which is kind of interesting question. Does ultra-scaled FDSOI make sense as the technology of the choice, or is there too much digital processing that is needed for phased arrays that may seek for 14 nanometer or even 7 nanometer, 5 nanometer technologies?
That's an interesting.
The direction of the technology.
Yeah. That's an interesting question because that really depends on the architecture choice. So let me take that question in the first question is FDSOI, does it make sense? Uh, I think FDSOI could be a good choice. I think a lot of the work on stacked PAs takes advantage of the FDSOI process for implementing it because it eliminates one of the diodes, which put if you do it in if you do a stacked PA in a bulk CMOS process, then the drain to substrate interface still sees a large stress even if you place the cascode device in a deep end well. So I think this paper or there are other papers on stacked PAs that take advantage of the SOI process. And SOI also has the advantage that depending on what SOI process you're using, I think that the key for SOI was to add that insulator so that you could reduce your leakage current. So SOI is a digital friendly process as well. So there are benefits of going to SOI, but I wouldn't say that's the only choice that is available. The second part of your question was is the amount of digital processing in the phased array chip, does it make sense to go to the more advanced technology node, say a 14 or so? So that depends on the degree of integration that is being implemented. Like as an example, if you go with architecture option 1, where it is just a beamformer IC with the LNA PA and the phase shifter, then I don't see a strong motivation for going there. There's only going to be loss here. First of all, you have a large number of elements. The cost is going to really shoot up because these advanced technology nodes are expensive, and the amount of digital processing here is just register read writes and maybe some. This would not justify it. If you're going to architecture, say architecture option 2 or 3, then there is a case to build. I still would say that it's not as strong. It depends on how much calibration is implemented in the system. If the IP developed is very digital intensive, requiring say microcontrollers and other circuits, then there might be a case to build. But I would say the main driving force is still going to be what sort of PA can you implement. So the processing, even with a microcontroller or other digital sections on a phased array chip, could be low speed. There's nothing in the standard that requires very high frequency decision making in a phased array chip. So, but again, these things change with time as the number of algorithms, as the standard become more complicated, the algorithms become more complicated, then processing takes a bigger role. So, yeah.
Yeah, I think this is kind of a trade-off that we have, and it does make sense that it is driven by the PA from the beginning. Yeah. There is another question related to TX. So I think you emphasize on the TX, so people are excited with that. So the question is, how critical is the TX power matching across the element in a phased array? And what impairments results from mismatched power? And is it easy to calibrate out the mismatch? So it's related to the phased array mismatch, element to element mismatch, and what is the effects and so on. Yeah.
Okay, so yes, it is important. So the whole assumption that if you have n elements with a power p, then you get a total power of say n square p depends on the fact that all elements have equal power. Now, but I guess that's an obvious answer. The question was like, what's the impact of having this mismatch? So there I see a few problems. First is when you try to go for uh, when you try to really push down the EVM floor, then you're invariably going to depend on some form of digital predistortion. So if you have one element, then you calibrate it, you find what you send a known signal, you find your DPD coefficients, and you're done. But if you have n different elements and they have a gain variation, now if you depending on how you develop your algorithm, how are you going to account for the fact that you have gain mismatch, you might have a phase mismatch between these different paths. So as your variation increases, then the effectiveness of your DPD reduces. So whatever benefit you could potentially gain from this approach goes down. So it makes sense to come up with some form of an algorithm to some form of a circuit which can reduce the amount of gain mismatch. The second is, so that's the first, DPD becomes less effective. The second is, if you have, say, you're assuming all four elements to have a power P, let's say the path to path gain variation is 2 dB, plus minus 2 dB. So you have two elements, one is P plus 2, another is P minus 2. So what happens is the circuit that drives your distribution network now is either overdriven or underdriven, because either you're overdriving your one of your PAs and then your EVM gets messed up, or you're underdriving the PA and you don't get your output power. So ways to mitigate this are obviously highly sought after, but then the challenge is that at higher frequencies, you need to have multiple gain stages. So let's say you take a 3-stage PA. So now you have path 0 with 3 stages and you have path 1 with 3 stages. So now you will have random variation, and as you increase the number of stages, then your amount of variation increases. So if I take a 10-stage PA, the total gain variation will be larger than a 1-stage PA. So higher frequencies results in more gain stages. More gain stages results in larger variation. So two paths on the same chip will have a smaller power match. What can you do about it? I guess that's just a design choice. The standard mismatch reduction techniques are known. You try to use non-minimum length devices wherever you can to reduce the variation. Shared bias circuitry, reduce systematic mismatch in the distribution paths. And also some form, I think there was a paper at ISSCC last year where, or maybe I read it somewhere else, where they had more calibration. They were trying to measure the current and try to add a calibration step to match the gain between the different stages. So there are different. The question was good, because I think that this is definitely a genuine problem that you will see when you scale this across millions of parts. But I think the solution is best practices in terms of gain matching and maybe some at an algorithm level.
Yeah, and if one of the transmitters, as you were mentioning, not giving the correct kind of power, like your beam will start being like the angle will start to be changing, and this will be like depending on the angle, the beam angle that you have, it will be kind of a sort of something that needs to be taken care of.
Yeah.
Yeah. I think Yeah, I have a question about the envelope tracking. This is kind of pushing the PEA, the efficiency of the PA.
Mhm.
So what directions do you think can be done, especially with the higher modulation bandwidths? Because in 5G, the higher modulation bandwidths, like the modulation bandwidths are larger and larger, and this can be an avenue for like relaxing the trade-off of PA, TX, RX, and so on. Yeah.
Yeah, I think if so here I just have to put this is kind of like a bit of future gazing at this point, but LTE definitely went in that direction. If you think of it, envelope tracking started as a research area, but then it became fairly standard in terms of most LTE systems to improve efficiency, to have envelope tracking supply modulators driving the PA. But the bandwidths were of a completely different magnitude. We were talking about like maybe signal bandwidth of 20 megahertz, 40 megahertz. Now we're talking about 400 megahertz, 800 megahertz. From what I've been reading up till now, I don't see a clear direction of how to get very such wideband envelope modulators out yet. So I even in publications I haven't seen that yet. But maybe that's the way of the future. There are obviously a lot of smart people working on this, so we might see something. But yeah, I think that's the future. But I haven't seen anything yet to convince me that it's there already there.
Yeah, yeah, me too. Okay, I think with that, I think the presentation today was very well attended. Like it's almost like or more than 100 attendees. I didn't check I checked that during the presentation. People are very interested in the topic, and would like the IEEE San Diego chapter would like to thank you very much for your presentation and all of this good kind of insight and preparing this material for the chapter and the IEEE community. And with that, yeah, I think we are concluding, and thank you very much for your time. And thanks all for
Thank
your
you.
time.
Thank you so much for the opportunity. Thank
No
you.
problem.